Welcome, seekers of knowledge, to Vibing Science. Tonight, we embark on a profound journey into the unseen heart of our planet, the ocean's temperature. It is a silent force, shaping everything from global climate to the very breath of marine life, a story whispered across billions of years. Prepare to drift into the depths of understanding as we uncover the profound secrets held within the water's thermal embrace. Before we plunge, please take a moment to like this video, share it with those who seek wonder, and leave a comment below. Your engagement fuels our exploration. Now relax, focus, or simply drift to sleep as we begin. The ocean, a vast and mysterious realm, holds within its depths a tapestry woven from the threads of temperature. From the shimmering surface where sunlight dances to the abyssal plains cloaked in perpetual darkness, temperature dictates the very essence of marine life, the rhythm of global climate, and the silent, powerful currents that traverse our planet. It's a crucial parameter, constantly shifting, yet fundamentally influential. Imagine, for a moment, the sun's golden touch upon the tropical seas. Here, where the sun reigns nearly overhead, the surface layers can warm to an astonishing 30 degrees Celsius, a balmy embrace for countless creatures. Now, drift mentally towards the frigid poles, where the ocean's surface meets the encroaching sea ice. Here, the temperature plunges to a chilling -2 degrees Celsius, a stark, profound contrast. These extremes are not mere curiosities. They are foundational elements in the intricate dance of our planet's climate. But the ocean is far from uniform. Its temperature, like its salinity, varies dramatically with depth, geographical location, and the relentless march of seasons. The warm, sun-kissed surface waters often boast a higher salinity, a testament to evaporation's subtle hand. Descend deeper, or venture into the polar reaches, and you'll find cooler, often fresher waters. The deep ocean, a world unto itself, makes up approximately 90% of the ocean's total volume. This colossal body of water is characterized by an almost astonishing uniformity. Imagine a vast, cold reservoir, where the temperature rarely deviates from a narrow band of 0 to 3 degrees Celsius. It's a realm of immense pressure and perpetual twilight, yet its consistent chill plays an indispensable role in the global climate system. Here, salinity hovers around 3.5%, a constant in a world of variables. This interplay of temperature and salinity drives one of the most magnificent and monumental processes on Earth, the thermohaline circulation. Picture a grand conveyor belt of water, constantly in motion, spanning the entire globe. It's a circulation fueled by differences in density, which are themselves born from surface heat and the infusion of fresh water. Warm surface currents, born in the tropics, embark on a long journey away from the equator. As they travel, they gradually cool, losing their warmth to the atmosphere. This cooling makes the water denser, causing it to sink into the abyssal depths. Once submerged, this cold, dense water embarks on its return voyage, creeping back towards the equator as a deep-sea current, only to eventually well up again, completing its timeless cycle, bringing nutrients and energy from the deep back to the surface, and absorbing heat and carbon from the surface back into the depths. This silent, powerful engine is a linchpin of Earth's climate, a testament to the interconnectedness of ocean, atmosphere, and life itself. When we speak of ocean temperature, we often consider it broadly, encompassing the entire water column. However, it's also a term that can be used more specifically to refer to temperatures away from the surface, synonymous with what we call deep ocean temperature. These deeper waters, more than 20 meters below the surface, exhibit regional and temporal variations that significantly influence the ocean's heat content and its stratification, the layering of water by density. And it is here, in these profound depths, that we witness some of the most concerning impacts of our changing climate. It is now unequivocally clear that our oceans are warming. This warming, a direct consequence of human-caused climate change, is not only accelerating but is penetrating deeper than ever before. The upper ocean, the first 700 meters, is experiencing the most rapid temperature increase. Yet, this warming trend is far from superficial. It extends throughout the ocean's vast expanse. The year 2022, for instance, marked a grim milestone. The global ocean recorded its highest temperatures ever documented by human observation. This unprecedented warmth is a stark indicator of the profound shifts occurring within our planet's most vital heat sink. The temperature of the ocean, whether at the sunlit surface or in the frigid abyss, works in concert with dissolved oxygen concentrations. These two parameters are profoundly influential, shaping everything from the ocean's primary productivity, the very base of the marine food web, to the intricate oceanic carbon and nutrient cycles, and ultimately, the health and distribution of entire marine ecosystems. They are the unseen architects, working alongside salinity and density to control a myriad of fundamental processes, the delicate balance between mixing and stratification, the direction and strength of ocean currents, and the grand, global circulation system that is the thermohaline circulation. To understand the full scope of this warming, scientists rely on a crucial metric: ocean heat content. This isn't just a simple surface temperature reading. It's a meticulous calculation derived from ocean temperatures measured at various depths, providing a comprehensive picture of the vast amount of energy absorbed by the global ocean. It's a testament to the ocean's role as the Earth's primary heat sink, absorbing over 90% of the excess heat trapped by greenhouse gases. Measuring this colossal, dynamic system is a formidable challenge, requiring ingenuity and sophisticated technology. Below the sea surface, pinpointing the specific depth of measurement is paramount, for temperature can vary dramatically, especially during the day. Imagine a calm, sunny day with minimal wind. The sun's warmth can create a thin, warm layer at the very surface, leading to steep temperature changes as you descend just a few meters. Scientists refer to these strong, daily vertical temperature gradients as a diurnal thermocline. The fundamental technique for probing these depths involves lowering a device known as a CTD. This acronym stands for conductivity, temperature, and depth, and it does precisely that. It continuously measures these three critical parameters. As the CTD descends, it electronically transmits its data back to a research ship via a conducting cable. Often, this device is mounted on a robust frame that also holds bottles for collecting water samples at specific depths, allowing scientists to gather a comprehensive snapshot of the ocean's chemical and physical properties. In recent years, since the 2000s and 10s, autonomous vehicles have revolutionized oceanographic research. Gliders and mini-submersibles, equipped with the same CTD sensors, now operate independently of research ships, silently traversing vast expanses of the ocean, gathering invaluable data over extended periods. Scientists can also deploy CTD systems from moorings, fixed buoys anchored to the seafloor, or even attach them to marine mammals like seals, transforming these creatures into living data collectors. For these autonomous methods, telemetry allows the data to be transmitted back to shore, providing continuous insights into the ocean's ever-changing thermal landscape. For sea surface temperature, the near-surface layer, measurements can be taken using traditional thermometers or, more extensively, through satellites employing spectroscopy. Weather satellites have been instrumental in determining this parameter since 1967, with the first global composites becoming available in 1970. The Advanced Very High Resolution Radiometer, or AVCHR, is a widely used instrument for measuring sea surface temperature from the vantage point of space, providing broad, consistent coverage across the globe. Beyond the CTD, a suite of other devices has contributed to our understanding of ocean temperatures at different depths. Historically, the Nansen bottle was used to collect water samples at specific depths, allowing for later temperature analysis. The bathythermograph, a mechanical device, would record temperature against depth as it was deployed. And in a more advanced approach, Ocean acoustic tomography uses sound waves to infer temperature variations over large ocean regions. Moored and drifting buoys, like those deployed by the Global Drifter Program and the National Data Buoy Center, continually measure sea surface temperatures, forming a critical network of real-time data. The World Ocean Database Project stands as the largest repository for temperature profiles from all the world's oceans, a testament to decades of tireless scientific effort. And looking to the future, a small test fleet of deep Argo floats aims to extend our measurement capabilities down to approximately 6,000 meters. Once fully operational, this network will accurately sample temperature for the majority of the ocean's immense volume, painting an even more complete picture of its thermal state. On ships and buoys, the most frequent measurement techniques involve thermistors and the venerable mercury thermometers. These traditional tools, often deployed in buckets dropped over the side of a ship for surface readings or attached to Nansen bottles for deeper measurements, remain vital components of oceanographic research. All these measurements, all this data, tell a consistent story. The ocean is warming. The cause of these profound shifts is clear. The warming of Earth due to human-caused emissions of greenhouse gases, such as carbon dioxide and methane. Growing concentrations of these gases are increasing Earth's energy imbalance, driving up surface temperatures across the planet. And the ocean, being the vast absorbent body it is, takes up the vast majority of this added heat, leading to the escalating ocean temperatures we are now witnessing. This warming brings with it a cascade of physical effects, each with far-reaching consequences. Higher air temperatures warm the ocean surface, leading to greater ocean stratification. Imagine layers of water, now less likely to mix. This reduced mixing stabilizes warm water near the surface, essentially trapping it there, while simultaneously hindering the circulation of colder, deeper waters. This reduced vertical mixing has a critical implication. It lessens the ocean's ability to absorb heat from the atmosphere, meaning a larger fraction of future warming will be directed towards the atmosphere and land, exacerbating terrestrial climate change. Furthermore, this stratification reduces the upwelling of nutrient-rich deep waters to the surface, impacting the productivity of marine ecosystems, potentially leading to declines in fish populations and diminishing the ocean's capacity to store carbon. Another dire consequence of warming is ocean deoxygenation. Warmer water, fundamentally, cannot hold as much dissolved oxygen as cold water. Coupled with increased thermal stratification, which reduces the supply of oxygen from surface waters to deeper layers, this leads to a further decrease in the water's oxygen content. The ocean has already lost oxygen throughout its water column, and we are witnessing the expansion of oxygen minimum zones worldwide. These dead zones are a growing threat to marine life, suffocating countless species that depend on dissolved oxygen for survival. Finally, warming ocean temperatures are fundamentally altering ocean currents. These currents, driven by varying temperatures associated with sunlight and air temperatures at different latitudes, as well as prevailing winds and the different densities of saline and fresh water, are the lifeblood of our oceans. Air warms and rises near the equator, then cools and sinks further poleward. Near the poles, cool air sinks, is warmed, and rises as it travels equatorward. This complex interplay of sinking and upwelling, combined with the wind's driving force on surface water, orchestrates the global circulation of ocean water. However, global warming is profoundly altering these processes, particularly in regions where deep water forms, potentially disrupting the delicate balance of the thermohaline circulation and triggering unpredictable shifts in global climate patterns. The story of ocean temperature is not just a tale of the present or the future. It also echoes through the deep past, revealing how ancient ocean temperatures have shaped life and Earth itself. Scientists believe that in the Precambrian period, 2 to 3.5 billion years ago, the sea was significantly hotter, perhaps between 55 and 85 degrees Celsius. Reconstructions based on oxygen and silicon isotopes from rock samples, and even reconstructed proteins from ancient organisms, paint a picture of an early Earth far warmer than today. By 1 billion years ago, these temperatures had cooled to a milder range of 10 to 40 degrees Celsius. Even the monumental Cambrian explosion, approximately 538 million years ago, a pivotal event in the evolution of life, is intertwined with ocean temperatures. Scientists believe that sea surface temperatures during this period reached around 60 degrees Celsius. Such temperatures are well above the upper thermal limit of 38 degrees Celsius for modern marine invertebrates, suggesting that the conditions for that major biological revolution were profoundly different from anything we see today. Later, during the Cretaceous period, from 100 to 66 million years ago, average global temperatures soared to their highest levels in the last 200 million years. This was likely due to the configuration of the continents during that era, which allowed for improved oceanic circulation, discouraging the formation of large-scale ice sheets. An oxygen isotope database further reveals at least 7 significant global warming events in the geological past, including periods during the Late Cambrian, Early Triassic, Late Cretaceous, and the Paleocene transition. During these epochs, the surface of the sea was an estimated 5 to 30 degrees Celsius warmer than it is today. These ancient warming events offer a profound, if sometimes unsettling, context for the changes we are witnessing in our oceans today. They remind us that the Earth's climate has always been dynamic, but the current trajectory, driven by human activity, represents a departure from the natural cycles that have shaped our planet's past. Welcome back, cosmic voyagers, to another deep dive into the silent, intricate workings of our world. Tonight, we turn our gaze, or rather, our ears, to a crisis unfolding beneath the waves, a profound shift in the very heartbeat of our planet, the silent crisis of ocean warming. For millennia, the oceans have been the grand regulators of Earth's climate, vast reservoirs of heat and life. Their temperatures dictating everything from the subtle sway of currents to the sprawling empires of marine habitats. We've spoken about the ocean's thermal tapestry, from the shimmering surface to the abyssal depths, how a dance of solar radiation, geographical whispers, and seasonal size create a liquid world of incredible variability. But now, this delicate balance is being irrevocably altered. The oceans are warming, and the rate of this warming is not just increasing, it is accelerating with an alarming intensity. Imagine a fever slowly but relentlessly gripping an immense body, a fever that has profound, cascading impacts across our entire global ecosystem. Let's begin by understanding the scope of this transformation. The ocean, particularly its upper layers, roughly the first 700 meters, is absorbing an astonishing amount of the excess heat trapped by greenhouse gases in our atmosphere. This upper ocean is warming at an unprecedented speed, a trend that began subtly but has now permeated even the deepest, most stable parts of our liquid world. In fact, 2022 marked a grim milestone. The global ocean recorded its hottest temperatures ever documented by human observation. This isn't just a record. It's a stark indicator of a system under immense stress. This warming isn't uniform, of course, just as the ocean itself is not monolithic. We've discussed how deep ocean water, making up about 90% of the ocean's volume, typically maintains a remarkably stable, frigid temperature between 0 and 3 degrees Celsius, with a consistent salinity of around 3.5%. These vast, cold, salty depths are the planet's thermal anchors. But even these ancient, deep waters are now feeling the encroaching warmth, a testament to the sheer scale of the heat being absorbed. Consider the intricate dance of ocean heat content, a crucial metric calculated by measuring temperatures at varying depths. This content is soaring, a direct consequence of human-caused emissions of greenhouse gases like carbon dioxide and methane. These invisible gases, products of our industrial age, amplify Earth's energy imbalance, relentlessly driving surface temperatures higher. And the ocean, being the massive heat sink that it is, has taken up the lion's share of this added energy, pushing its own temperatures ever upward. The main physical effects of this warming are far-reaching and interconnected, creating a ripple effect that touches every corner of our blue planet. One of the most significant consequences is increased ocean stratification, a term that might sound innocuous but carries immense implications. As higher air temperatures warm the ocean surface, the lighter, warmer water tends to stay on top, forming a more stable, less mixed layer. This stratification acts like a thermal blanket, reducing the vital exchange between surface and deeper waters. Imagine a vast, multi-layered liquid world where the upper, sunlit layers normally mingle with the colder, nutrient-rich depths. This mixing is crucial. It's how vital nutrients are brought up from the abyss to fuel the primary productivity in the surface waters, the very foundation of the marine food web. It's also how oxygen, produced at the surface through atmospheric exchange and photosynthesis, is transported to the deep. But with increased stratification, this vital circulation is stifled. The warm surface waters become less dense, creating a barrier that prevents cooler, deeper waters from rising and oxygen-rich surface waters from sinking. This means less oxygen reaching the deep ocean, a process we call ocean deoxygenation. Warmer water, by its very nature, can hold less dissolved oxygen than cold water, compounding the problem. We are already witnessing an expansion of oxygen minimum zones worldwide, vast oceanic dead zones where life struggles or simply cannot exist. This reduced mixing has other profound effects. It limits the ocean's capacity to absorb more heat, directing a larger fraction of future warming back towards the atmosphere and land. It also impacts the ocean's ability to store carbon, further exacerbating climate change. And for the marine life that relies on these nutrient upwellings, particularly fish in the upper ocean layers, a decrease in available nutrients spells disaster for entire ecosystems. Then there's the profound impact on ocean currents. These majestic rivers within the sea are driven by a complex interplay of sunlight, air temperatures, prevailing winds, and the differing densities of saline and freshwater. The thermohaline circulation, that colossal global conveyor belt we spoke of, is a prime example, driven by density gradients created by heat and freshwater fluxes. Warm surface currents cool as they journey away from the tropics, becoming denser and sinking, moving as deep-sea currents before eventually welling up again. Global warming is disrupting this delicate ballet. Changes in temperature and density, particularly in regions where deep water is formed, are altering these currents. Imagine the global conveyor belt slowing down or rerouting entirely. Such a shift could have catastrophic consequences, not only for marine life that depends on these currents for nutrient distribution and migration, but also for global climate patterns, potentially leading to more extreme weather events and further disrupting the delicate balance of our planet's heat distribution. The energy available for tropical cyclones and other powerful storms is likely to increase, fueled by warmer ocean waters. The science of measuring these changes is an ongoing marvel of human ingenuity. From the earliest mercury thermometers lowered over the sides of ships to the sophisticated CTD devices, measuring conductivity, temperature, and depth that continuously transmit data from the deep, we are gathering an increasingly comprehensive picture. Autonomous vehicles like gliders and mini-submersibles, equipped with these same sensors, now silently patrol the ocean, collecting invaluable data independently of research vessels. Satellites with advanced radiometers like AVCHAR have provided global sea surface temperature composites since the 1970s, offering a bird's-eye view of this silent warming. The Argo program, a global array of over 4,000 robotic floats, is at the forefront of this effort, constantly measuring temperature and salinity throughout the upper 2,000 meters of the ocean. A newer, deep Argo fleet is being deployed to extend this critical measurement capability down to 6,000 meters, aiming to sample the vast majority of the ocean's volume with unprecedented accuracy. These tireless sentinels of the deep are providing us with the raw data that paints this sobering picture of a warming ocean. The evidence is overwhelming, and the message is clear. The silent crisis of ocean warming is not a distant threat. It is a present reality, unfolding beneath the waves with profound implications for every living thing on Earth. As we continue our journey through the wonders of science, understanding this crisis becomes not just a matter of scientific curiosity, but an urgent call to awareness and action. Next, we will journey back through time, exploring the echoes of the deep past and how ancient ocean temperatures shaped life and Earth itself, providing a crucial context for the changes we observe today. So, settle in and prepare for another voyage into the depths of knowledge, where every whispered fact holds the weight of our shared future. For all its profound mysteries, the ocean is also a living archive, holding within its depths the echoes of Earth's ancient past. To truly understand its present and future, we must cast our minds back, far beyond the reach of human memory, to times when our planet was an almost alien world. The story of ocean temperature isn't just about today's warming trends. It's a saga stretching back billions of years, a narrative etched in the very bedrock of our planet and the fossils of primordial life. Imagine, if you will, the Precambrian period. This isn't just ancient history. It's a vast, incomprehensibly long stretch of time, encompassing nearly 90% of Earth's entire existence. Picture a young Earth, still finding its rhythm, its atmosphere nascent, its land masses in constant, violent flux. Scientific reconstructions, painstakingly pieced together from oxygen and silicon isotopes locked away in ancient rocks, paint a truly astonishing picture of the oceans during this epoch. These reconstructions suggest that, between 2 and 3.5 billion years ago, the primordial ocean was a cauldron. Its temperature is believed to have soared to a blistering 55 to 85 degrees Celsius. Think about that for a moment. Water hot enough to scald, far beyond anything we consider habitable for complex life today. It was a world fundamentally different, where the very chemistry of life was forged in these searing waters. As the eons slowly, glacially, turned, this intense heat gradually began to dissipate. By 1 billion years ago, the planet had cooled significantly, and its vast oceans settled into a more temperate, albeit still warm, range of 10 to 40 degrees Celsius. This ancient warmth isn't just theoretical. The very proteins found in the reconstructed organisms from the Precambrian era carry the indelible signature of this hot past, providing biological corroboration to the geological evidence. Life, in its earliest forms, adapted to thrive in conditions that would be lethal to most modern organisms. Then came one of the most pivotal moments in the history of life on Earth, the Cambrian explosion. Approximately 538.8 million years ago, in a geological blink of an eye, an unprecedented diversification of multicellular life occurred. The fossil record suddenly burst forth with an array of complex organisms, many of them ancestors to the myriad species we see today. But here's the astonishing twist. This biological revolution, this explosion of form and function, is believed to have taken place when sea surface temperatures reached an astounding 60 degrees Celsius. Now, pause and consider the implications of that temperature. For modern marine invertebrates, the upper thermal limit for survival is around 38 degrees Celsius. 60 degrees is not just uncomfortable. It's a death sentence for most of them. This presents a profound scientific puzzle. How could such a massive biological revolution, demanding intricate biochemical processes and delicate cellular structures, have unfolded in waters hot enough to cook modern seafood? It challenges our very understanding of the adaptability of early life and the conditions under which evolution can accelerate. It hints at a world where the rules, as we understand them today, were fundamentally different, and life found ways to flourish against odds that seem insurmountable from our current perspective. Moving forward in time, to the later Cretaceous period, from roughly 100 to 66 million years ago, we find another peak in Earth's thermal history. Average global temperatures during this time soared to their highest levels in the last 200 million years or so. This wasn't some localized anomaly. It was a planetary phenomenon, likely a direct consequence of the configuration of the continents during this era. The arrangement of land masses profoundly influenced ocean currents, allowing for a far more efficient global circulation of heat. This global warmth discouraged the formation of large-scale ice sheets at the poles, contributing to higher sea levels and a world without significant polar ice caps. The oceans, far from being the deep, cold reservoirs we know today, were vastly warmer, influencing everything from marine ecosystems to atmospheric moisture. But these aren't isolated incidents. A comprehensive database built from oxygen isotopes, preserved in ancient sediments and fossils, reveals a recurring pattern throughout Earth's history. It indicates at least 7 distinct global warming events in the geological past. These include significant periods such as the Late Cambrian, Early Triassic, Late Cretaceous, and the profound Paleocene thermal maximum. During these warming periods, the surface of the sea was, on average, between 5 and 30 degrees Celsius warmer than it is today. These ancient thermal excursions are not just fascinating footnotes in Earth's history. They are vital lessons. They demonstrate the planet's profound capacity for change, the dynamic interplay between geology, atmosphere, and ocean, and the incredible resilience, and sometimes fragility, of life. Each warm epoch left an indelible mark on marine ecosystems, driving extinctions, spurring adaptations, and reshaping the very course of evolution. Studying these ancient temperatures helps us contextualize our current predicament. While the causes of past warming events often differ from the human-driven warming we are experiencing today, the effects on ocean chemistry, currents, and life provide crucial insights. They show us how ecosystems respond to rapid thermal shifts, how ocean stratification increases, how oxygen levels deplete, and how species migrate or perish. The deep past, therefore, is not merely history. It is a profound cautionary tale and a rich repository of natural experiments, offering invaluable clues to navigate the challenges of a warming ocean in our own time. The ocean's memory is long, stretching back to a time when its waters boiled with the genesis of life, to eras when vast marine reptiles patrolled seas warmer than any we know. These echoes of the deep past remind us that ocean temperature is not a static variable, but a dynamic force that has continually shaped our planet, dictating the very conditions for life itself. And in understanding these profound historical shifts, we gain a deeper appreciation for the silent, yet accelerating transformation occurring within the ocean's thermal tapestry today. Our journey through the ocean's thermal tapestry has brought us to a fascinating juncture. How do we actually know what the ocean's temperature is? This invisible data, these subtle shifts in degrees, hold profound truths about our planet, its past, and its future. The science and art of measuring ocean temperatures is a testament to human ingenuity, a relentless pursuit of understanding the vast, liquid heart of our world. Imagine standing on the deck of a research vessel, the waves gently rocking beneath you, and contemplating the impossible task of measuring the temperature of an entire ocean, from its shimmering surface to its crushing, silent abyss. It sounds like science fiction, yet we've developed an intricate array of tools and techniques to do just that. At the most fundamental level, we understand that ocean temperature is not a single, monolithic number. It's a dynamic, ever-changing spectrum. It varies not just with geographical location and season, but most dramatically with depth. This layered complexity is what makes its measurement so crucial. Surface waters, kissed by the sun, can soar above 30 degrees Celsius in the tropics, where the sun stands almost directly overhead. Yet, as you venture towards the poles where sea ice reigns, the equilibrium temperature can plummet to around -2 degrees Celsius. But what about the depths? Venture far below that sun-warmed skin, beyond the influence of daily solar radiation, and you enter a realm of remarkable uniformity. Deep ocean water, a vast reservoir making up about 90% of the ocean's volume, maintains a surprisingly consistent temperature, hovering steadily between 0 and 3 degrees Celsius. This cold, salty mass is a crucial player in the planet's climate system, a slow-moving, immense engine that drives global ocean currents. Understanding these variations, both subtle and stark, requires more than just a thermometer dropped over the side of a boat. For near-surface measurements, the most traditional methods might indeed involve a simple mercury thermometer, perhaps nestled in a bucket of seawater. But even here, precision is key. Satellites equipped with advanced radiometers, like the Advanced Very High Resolution Radiometer, have revolutionized our ability to measure sea surface temperature from space, offering wide-ranging, continuous data since the late 1960s. These orbital eyes provide invaluable global composites, allowing scientists to track broad patterns and anomalies across vast stretches of ocean. Yet, the true challenge, and perhaps the most intriguing aspect of ocean temperature measurement, lies beneath the surface. Here, the variations can be dramatic, especially during periods of low wind and abundant sunshine, which can create what scientists call a diurnal thermocline, a sharp vertical temperature gradient that forms and dissipates within a single day. To penetrate these layers, we rely on sophisticated instruments. The cornerstone of modern deep ocean temperature measurement is a device known as a CTD. This acronym stands for conductivity, temperature, and depth. A CTD is typically lowered from a research ship on a conducting cable, continuously sending data back to the surface in real time. Imagine a high-tech probe descending into the abyss, wirelessly whispering its findings back to the anxious scientists above. Often, this device is mounted on a robust frame, accompanied by water sampling bottles, allowing researchers to collect physical samples at precise depths for further analysis. This combination provides a comprehensive snapshot of the ocean's properties at various levels. But research ships are not the only platforms for CTDs. In an increasingly autonomous world, robotic gliders and mini-submersibles have emerged as powerful tools. These independent vehicles, equipped with the same CTD sensors, can operate without direct human intervention from a ship, roaming the ocean for extended periods, gathering invaluable data, and transmitting it back to scientists via telemetry. Even seals fitted with miniature CTD sensors have become unlikely, yet incredibly effective biological data collectors, providing unique insights into polar waters. Beyond CTDs, other specialized instruments contribute to our understanding. The Nansen bottle, a relic of earlier oceanography, was designed to collect water samples and measure temperature at specific depths. The bathythermograph, another historical tool, provided a continuous temperature profile as it was lowered through the water column. And then there's ocean acoustic tomography, a fascinating technique that uses sound waves to infer large-scale temperature variations over vast distances, leveraging the fact that sound travels at different speeds through water of different temperatures. Perhaps one of the most ambitious and transformative efforts in ocean temperature measurement is the Argo program. This global array of autonomous profiling floats, roughly the size of a telephone pole, drifts with the currents, descending to depths of 2,000 meters, and then periodically surfacing to transmit its data via satellite. Each float completes a cycle every 10 days, collecting temperature and salinity profiles across the world's oceans. Since its inception in the early 2000s, Argo has provided an unprecedented wealth of data, dramatically improving our understanding of ocean heat content and its role in climate change. A small test fleet of deep Argo floats is now pushing these boundaries even further, aiming to extend measurement capabilities down to an astonishing 6,000 meters, effectively sampling the majority of the ocean's volume. All of this painstakingly collected data funnels into monumental repositories like the World Ocean Database Project, the largest database for temperature profiles from all of the world's oceans. These vast digital libraries are the collective memory of our planet's aquatic heat, allowing scientists to track trends, identify anomalies, and build increasingly accurate models of oceanic processes. The most frequent measurement techniques, particularly on ships and buoys, still rely on thermistors and mercury thermometers, a testament to the enduring accuracy and simplicity of these instruments when used correctly. Whether dropped over the side in a bucket for surface readings or attached to Nansen bottles for deeper measurements, these foundational tools continue to play a vital role in our understanding. This intricate web of observation, from simple thermometers to sophisticated satellite sensors and autonomous floats, paints an ever-clearer picture of the ocean's thermal state. And what this picture increasingly reveals is a profound and concerning trend. The oceans are warming, not just the surface, but throughout their vast depths. This warming, driven by human-caused greenhouse gas emissions, is not merely an abstract scientific finding. It is a fundamental shift with cascading global impacts. The upper ocean, specifically the top 700 meters, is warming at the fastest rate, but the warming trend extends throughout the entire ocean column. In fact, 2022 marked a grim milestone. The global ocean was the hottest ever recorded by humans. Understanding how we measure these changes is as crucial as knowing the changes themselves. It is through this diligent, continuous monitoring that we confront the invisible truths of our planet's warming oceans, truths that will shape the very future of life on Earth. And so, our odyssey through the ocean's thermal mysteries concludes. I hope this journey has offered you new perspectives, perhaps even a moment of calm reflection on the intricate dance of our living planet. The story of ocean temperature is vast and ever unfolding, a testament to the delicate balance of Earth systems. If you found solace or enlightenment in these narratives, please consider liking this video, sharing it, and subscribing to Vibing Science for more deep dives into the universe's wonders. What aspects of our world or beyond would you like to explore next? Share your thoughts in the comments. Until our next expedition, keep exploring, keep questioning, and stay curious.